Today we'll be looking at some of the more advanced patterns in the Mosaic puzzle. Just a reminder, in a Mosaic puzzle, your goal is to color every cell in the grid, either black or white, such that every one of the numbered regions tells you the number of black cells that are in its neighborhood. Now, if you've got a cell here, let's say, the neighborhood of 3 would be this 3 by 3 region, but if you're on a edge, there's a 6 cell region, or if you're in the corner, there's a 4 cell region. We looked at the very simple ones, such as this 4 or 6, where the neighborhood is containing only 6 entries. Isolated 0, isolated 9. We also looked at some slightly more complicated ones. So there's 1 black in this region. The purple and blue must have at exactly 4, so you would immediately be able to deduce these. And similarly, anytime there's a +3, meaning you've got 2 orthogonally adjacent cells differing by 3, you can immediately deduce that the larger side has 3 and the lower side has 3 white. A similar property happens on the boundary of the world. So if you're on an edge, if you have a +2 in this case, you know that the combined number of blacks in the red and purple region is 1, and the number of blacks in the blue and purple region is 3. So it follows that there must be 2 here and 1 in the purple region. Otherwise you would violate the constraint that the purple and red can only have 1 in total. And a similar deduction occurs for all of these cases, but this one's even more obvious. Whoops. Like so. Now, it is in fact identical to the +3 rule here. It's just you have to treat the boundary of the board as just being a line of white cells. If you interpret it that way, then it's actually the same rule. But to do so, you would need to understand how to modify the counts. So that's what I'll talk about here. This is the main technique in Mosaic puzzles. So all of these sets of clues are in a sense identical. So the +3 rule would tell you can make this assignment. Anytime you see a white in the neighborhood of one of these numbers, but not in the neighborhood of the other number, you can actually treat that as being a modifier such that it adds to the number. So this 4 here has a white in its neighborhood that is not in the neighborhood of this 2, so you can actually treat this as being a 5. And black is subtractive. This black is in the neighborhood of 3, this red neighborhood, but it is not in the neighborhood of this 5, so you can actually treat this as subtracting from this 3 and giving you 2. So as soon as you see this, a +3, you can actually see this as being a +3 as well, but you wouldn't overwrite the fixed cells. So you can make all of these deductions immediately. So this one's a lot more obvious. There must be 2 blacks in the neighborhood of this 2. Since these are already white, the 2 must occur here, which means 2 of these cells must be black, which means that this would be white. And the subtractive rule holds here. So this is equivalent to a 2 due to this black being here, which means you can make analogous deductions, like so. Other advanced rules, let's see, you've got the +5 on the diagonal, so there can only be 1 black in this region, but the blue must have 6, which means all 5 of these external cells must be black, and then there's some black in here, which means that these would then be white. So that's another one of the advanced ones, and it is a +5 in general, so you could also make the same deduction in this case and in this case, where the final case is sort of obvious if you had 4, 9. Let's solve one of the hard-rated puzzles together. So first of all, you'd start with the zeros. Then you can use the +3 rule in several places. So 2 and 5 is +3, 3 and 6, 5 and 2, 4 and 1, 2 and 5, like so. This is equivalent to a 3 due to this, as well as these ones. This is equivalent to a 4 due to this white. gets you to here. 2 in the corner like this, you can deduce that this is also satisfied as soon as this one is, which gives you this. This is equivalent to a 5, which gives you these. So this will get 1 more in one of these positions, which will then satisfy this 2. Which gets you to here. This is equivalent to a 4 due to this, which gets you to here. This is satisfied. This just needed 1 more white around it. That's already satisfied, as you can see, and that solves the puzzle.